Hey everybody, welcome back to another Codeforces training. Today we're going to be talking about shortest paths. And it's a pretty important topic in graphs, as you know. So the basic problem we're going to be concerned with today is single source shortest path, which is stated as following. So we have a graph which can be either directed or undirected. And all edges, they have some weights, so they are weighted, right? Also, you can come across terms such as length of an edge, which is kind of obvious, and also a cost of length, which originates from road construction, I believe. All these terms are equivalent. They basically mean that there is a quantity, integer, or any other type of quantity associated with every edge. And edges can be both directed and undirected. So it depends on the problem. And we are also given some source vertex S. Also, you can come across terms such as start vertex or whatever. And we want to find shortest distances from vertex S to all other vertices. As simple as it gets. Well, the problem is kind of simple, but existing solutions are not particularly difficult, but not straightforward, let's put it this way. So let me pose a demonstration. We have, as you know, it's a Codeforces training, so we'll be covering a couple of problems today. Only 3 for today, but these are kind of good. They cover 3 basic algorithms that exist in SSP problem. Yeah, I guess I can make it kind of bigger, and also this part. All right, so the first algorithm we're going to be concerned with is, of course, Dijkstra. And we will first cover the basic version of Dijkstra, which actually works in big O of n squared, which you may think is not optimal because, n is the number of vertices, right? Because, of course, there exists a version of Dijkstra that runs in m times log n, where m is the number of edges, right? So you may think like, wait a minute. If we have an algorithm that runs in big O of n squared, and we have something like big O of m log n, or potentially even n log n if you know how to write Fibonacci heap, but it's kind of tricky, so we're not going to be covering this today. We have big O of m times log n. I think like, well, the reasonable bounds and the number of edges are, of course, the number of edges is kind of at least linear, right? And at most quadratic. And I know that you can divide by 2 here, but it doesn't really matter in terms of big O notation. So let us see for which values of m, which algorithm is going to be faster before we discuss any algorithm, so that we kind of understand what is good and what is not good, because it's tricky with graph problems. So there are 2 main types of graphs. So first type is dense graphs. Dense, right? Typically, one assumes that m is about the same size as n squared, right? So potentially you can have like something m equals to n squared over 4, so that's half of the edges is present roughly, or n over 6, or something quadratic, let's put it this way. A typical representation of these graphs is, of course, adjacency matrix. Here we have adjacency matrix. And it stores distances. So we have a vertex u and a vertex v. And the corresponding entry is distance from u to v. right? It makes sense to store graphs like that because regular data structures, so that a couple of vectors of equal lengths usually perform better. And if you take in roughly all the space, then it of course makes sense to store it like this. You don't have to worry about anything in particular. You can quickly access the length of the given edge, right? Just to, you have to follow 2 pointers basically. The first to this array and then to this entry. So for such graphs, version 1 will still work in quadratic time, but version 2 will work in big O of n squared log n. And if you have n, let's say approximately equals to 1000, and I say 1000 because it doesn't really make sense to have 10 to the fifth, or, well, you can have 10,000, right? Potentially, but you hardly can have something like 10 to the fifth here, because it's gonna be a time limit exceeded anyways. So if n equals something around 10,000, right? Then log n is what? Log n is roughly 14, I believe. So that's kind of unpleasant, because if we estimate, then this gets approximately 10 to the 9th, and because the second version of Dijkstra uses priority queue or sets, whatever you use, you have also some hidden constant. So it's not likely that this version will fit into 1 second time limit. In case of dense graphs. So for dense graphs, the first algorithm is definitely the way to go, and we'll cover it in a second. Now, there is also a different kind of graphs, which is of course sparse graphs. So we have sparse. Now, sparse is obviously not dense. I believe everyone knows this. And the common convention is something like m is significantly smaller than n squared. So common examples may include, I guess, m is approximately cn. In case of regular kind of tilings, for example, if you have a board, checked board, and you want to find shortest path in it, and probably c equals around 4, something like that, because every cell has four adjacent cells, right? So yeah, this kind of sparse graphs, it becomes kind of obvious that this will run faster than this, because log n is not also big, right? So once we have m smaller than n squared over log n, and it becomes reasonable to use the second version of Dijkstra. I'm not exactly sure what is the common agreement in English to pronounce Dijkstra. Possibly it's Dijkstra, but I believe that in Dutch it is correct to pronounce like Dijkstra. Kind of tricky, but choose whatever works better for you. Yeah, so for most reasonable sparse graphs, this condition obviously holds, and it makes sense to use the second version. And we will see that these two algorithms are not fundamentally different in nature. They just use different underlying data structures. So both algorithms will have some sort of distances array, right? Initial distance to the source is obviously 0, because we can do we don't need to make any moves to get from starting vertex to itself, right? And for all other vertices, the distance will be positive infinity. which I personally like to model in code by something like std numeric limits, right? Yes, you can see it somewhere here. I define a constant, which is numeric limits int max. Obviously, you can go with something like 1 billion, but be careful. Basically, what you want from k infinity is to be strictly significantly larger than any length of a valid path that can appear in your calculations. So if I'm sure that my distances fit into integer type standard, then I go with numeric limits int max. If I'm not sure, and it happens quite often, then I just go to long integers and it works all the time. Unless you do something stupid like I sometimes try to add 1 to infinity, it obviously results in negative infinity. So yeah, be smarter than me, don't do it, okay? I believe you can handle it. All right, so besides D, we also want some sort of used array, Boolean array, which will denote whether or not our algorithm has already processed some vertex, okay? And basically, we're going to process vertices one by one. And the specific order in which we're going to do that will ensure that we end up with a correct answer indeed. So on every iteration, we're going to be selecting the vertex which is not used. So used of v equals false. Originally, all vertices are not used, and we will mark them as used as we go. So once we select unused vertex with minimum distance to it, we mark it as used. Right? So we never process one vertex twice. And the reason why resultant complexity becomes big O of n squared is because if we have a pure array, then minimum selection unfortunately works in O of n. So clearly we have at least, well, we should have at least exactly one iteration per vertex. We're gonna have big O of n iterations. And also each iteration already costs big O of n. Combine them and you get the resultant complexity. After we select such vertex, we iterate over all outgoing edges. So VW is an edge outgoing from V somewhere else, right? And basically what we're doing is we're trying to improve distance to W as distance from, so we have some source vertex, right? We have V and we have an edge to W. Potentially at the current moment, we have a shortest path to W lies something like that. And we try to improve it by going from S to V first and then to W. So we clearly get something like this. So distance to W gets minimum of the current distance to W and a distance to V plus the length of the edge, clearly from V to W. And it's basically everything that goes on. So nothing more, that ensures that you're going to achieve minimum distances by the end of your n iterations. And the reason is because we process vertices in a specific order by choosing on every iteration the vertex that has minimal current distance. If you think about it, this condition ensures that once we process vertex v, the distance to v can never decrease. Why this happens? So suppose we later, suppose the shortest path is something like that, right? And we ended up with having a path like that. So why it can be the case? Well, if we process this vertex, no, okay, if the length of the blue path is smaller than that of a red one, then in particular the length of this path is shorter than the length of the red one, right? So it means that this vertex, whatever it's called, let's call it T, is processed by the algorithm before V. And obviously then we would have to make the relaxation, and this operation is called mean relaxation. Mean because we have mean, or there is also max relaxation in different scenarios, right? So if the distance to T is smaller than that to V, and we clearly have to process T before V, right? And then when we do relaxation, we effectively find the blue path. That's why we end up with having traversed all the shortest paths. And yeah, you can kind of make it more formal if you put everything in the context of mathematical induction. So you just state the same proposition clearly. It's after vertex gets used, the corresponding label gets the correct distance and won't change anymore. And you prove this fact in the setup of mathematical induction. So on the first iteration, it is obviously true because we select starting vertex, and then you use the fact that this vertex got the shortest path. Then when we do relaxation, this also gets this path. And because we iterate through all vertices that are closer to S than we kind of iterate through all shortest paths, potentially. Paths that are shorter than our red path. Okay, I hope it was clear. I mean, yeah, if you want to prove it like very formally, you can do it. I'm just giving some sort of intuition that I believe should be enough for you. Okay, so what are the problems with this algorithm? It provides a correct answer for sure, but it's kind of slow. And it's kind of slow because we select minimum in a very lazy fashion. All right, so we obviously there are better data structures to quickly select minimum and update elements, right? In particular, to decrease elements. Now, one may actually view like select mean and decrease key as the defining operation for a data structure called heap, or also known as a priority queue, which is of course implemented in standard library of C++. Yeah, it's very efficient because underlying structure is linear, so the heap is built over an array. There are a couple of invariants present that the data structure maintains, and it provides an interface, which is, let me clear some space for it, and we will see in a minute. We don't need this. So the heap, well, a C++ heap definitely provides a find mean operation. And it also obviously provides operations such as insert and actually extract mean. Right? Well, heaps in general also can provide operations such as decrease key. The complexities will change a bit for Fibonacci heaps, but you will get the running time of big O of n log n. But I personally haven't seen many people implementing Dijkstra on top of Fibonacci heap. Usually people just use priority queue of pairs, and yeah, if Dijkstra is the intended solution and you're not trying to trick the system by submitting something that is slower than expected, then priority queue is definitely the way to go. If you're trying to trick somebody, online testing environment by submitting Dijkstra when Dijkstra is not expected, there are a couple of tricks that can speed up heap by another 30%, I believe, or so. Now, currently we store the following values in the heap. It's like a distance to vertex is the key, and the value is the vertex itself. And well, one of the problems with heap is that you can't easily, with standard heap, is that you can't easily change the key. Right? Because you don't necessarily know where the key is. And heaps are good for finding minimum elements and providing fast access to minimum elements, but they are not very good at finding arbitrary elements. For arbitrary elements, of course, STD set is the way to go, but underlying structure of STD set is, of course, a tree, like I believe red-black tree. Potentially, you can have your own STDs or your own set that uses AVL tree, but I believe it still loses to heap just because of the underlying structure of heap is linear and so fast, thanks to random access memory, right? I know. Okay, so yeah, because standard heaps cannot delete elements by key, we sometimes, we don't delete actually, we just insert new pair if it's better. And when we come to this pair, we know it's should be discarded as a fake pair because the distance to vertex is not correct. So we already decreased the distance here and inserted the pair d, well, let's say like dv prime and v, right? And this distance newly inserted is smaller than this. So when we come to this, we just get to compare the first element of the pair with the current distance and say like, oh, if it's greater, then it's just some kind of old pair, and we shall discard it just like that. Yeah, so, and because of that reason, we actually end up using it most m elements in a heap, right? So actual running complexity is what? Big O of m log m, because we make around m operations with the heap, and each operation is for log of the size of the heap. But again, m is at most n squared, so log m is at most 2 times log n. So usually you won't see log m. You will see log n. Because it like the constant is at most 2, people don't usually care about that constant. So really what's going on is the same thing, which we iterate over outgoing edges. Just now, because of heap, we can quickly select vertex with minimum distance. And it makes things faster because when there are not too many edges, and this selection is faster than a naive selection just by iterating, looping over the array. Yeah, I believe we should work through some example. And let me check. We definitely have example problems here. Yeah, all right. We have some graph. Should definitely cover it. So the first problem will be just to implement Dijkstra. The input is what? A number of vertices, start, destination vertices, right? We have 3 vertices. First one is the source, second one is the destination. 1, 2, 3, and there are a couple of edges, so obviously distance from vertex to itself is 0. There is no edge from 1 to 2. There's edge from 1 to 3 of length 2. There's edge from 2 to 1 of length 3. There is no edge from 2 to 3. There is an edge from 3 to 2 of length 4. So let us draw the initial array looks like this, because first vertex is the start vertex, right? And second vertex is destination. Now, as you may notice, in this problem, we have a specific destination. In general algorithm, we don't, but of course, we can stop once the destination gets processed. But normally you don't have to. The difference is, let me put it this way. If you're doing a lot of Dijkstra searches, and probably you don't want a Dijkstra search, you want something like a float version, which computes in a cubic time, and quadratic memory, it computes all the shortest distances. So if you have multiple shortest path problem, and vector algorithm exist, if you have one Dijkstra, and it's unlikely that early stopping will save your life. Let me put it this way. I mean, my solutions, I didn't have to optimize like anything. I just implemented them in a very lazy fashion when we process Dijkstra to the end, and it runs comfortably in something like 200 milliseconds out of 2 seconds. So yeah, potentially you can have like 100 milliseconds, but I don't care as long as it's significantly below time limits. Yeah, so what goes on? This graph isn't particularly interesting because there are not too many edges, right? So let me add an extra edge. Let me deliberately make it of length 7. In a stupid Dijkstra, we will process these 2 edges outgoing from starting vertex and get the following array. So this is what we get after the first iteration. And we also know that first vertex is used. Then we select the vertex with minimum distance, which is 2. Well, I mean, index 2, vertex 3, right? And the distance to 3 is 2. Then we take a look at all outgoing edges. We have one outgoing edge of length 4, to vertex number 2, which is at index 1. We check 2 plus 4 is 6. 6 is better than 7, so we update. And we also mark last vertex as used. So now we have like second vertex, it has outgoing edges. These edges go back to already processed vertices. You can ignore them, you can process them as usual. Like, it won't make any difference. No distances will decrease. So on this next iteration, we just confirm that everything is fine. If, however, this edge had a length of 5, and here we would have 5, and despite 3 being the closest vertex, we would process third vertex first, right? But it won't change the distance because 2 plus 4 is bigger than 5. So we don't update. Then we process 5. So as you can see, like in different cases, whether or not the path is shortest by the number of edges, right? The algorithm works. And that's it. Now in second problem, I believe you don't have any specific questions about this example. It was kind of easy. Of course, in real problems, we have like 2,000 vertices, 10,000 vertices. Well, probably not 10,000 vertices because the input would be huge, right? It already has like 4 million entries. By the way, because it has so many entries, you definitely need fast input. Or actually, I believe fast input depends on the number of lines of input that you have. Okay, so yeah. I mean, it's not difficult to write fast input all the time, right? Especially when you're using a template. Okay. Well, the second problem is gain distances, but this time we have a huge graph of 70,000 vertices. Now, currently it's not treated as a huge graph. Huge graphs have like million vertices, but back in the day it was kind of huge. In current standard problems, you can expect something like 10 to the 5th vertices, 2 times 10 to the 5th vertices, and something between 3 to the 5th, 3 times 10 to the 5th edges, up to 1 million edges, I suppose. So this graph is definitely sparse because 7,000 squared is much bigger than 200,000, right? Around, I don't know how many times. I honestly don't know, around 25,000 times bigger. So yeah, there are really not all that many edges in the graph. And it obviously points us towards the sparse Dijkstra. We can work an example with sparse Dijkstra, but it will be essentially the same, only the data structure will change. Actually, let's do this. I mean, it's kind of instructive. Let us take our new graph. We have 4 vertices this time. Very good. At least it won't be as boring as 3 vertex graph, right? So it's from first to second of length 1, from third to fourth of length 5. And notice that this time we also have to output the path itself. Dexter is obviously suited for this. You can maintain the array of parents. So you will have 2 arrays, one for distances, one for parents, and parents are that on the shortest path. All right, so every time you do a successful min relaxation, you will have to update the parent, because your parent on the shortest path changes. And that's as simple as it gets. I mean, we will look at parents processing in this example specifically. And also notice that first page of this statements contains some theory. So you can definitely check this out if you don't have all that much time to watch an entire video. You can just read. And then watch the video if something was not clear in the theory. Okay, so we have an edge from 3 to 2 of length 2, from 4 to 1 of length 4. Oh, and this is also undirected graph. So everything I just drew is wrong because I have undirected edges. So you can travel anyway. You want to travel this way, fine. You want to travel this way, also fine. And this is how undirected graphs work. But you're given every edge only once because it makes no sense to make output larger without a good reason. Input larger. So when you insert an edge, you get inserted from first to second and also from second to first. So you insert the edge twice into your graph. And I will get back to all these technical details when we cover the code. I'm just working through examples so that you get the feeling of how the algorithms work. Yeah, we have parent array, we have distances. We want to travel from first vertex to third vertex. All right. Initially, distances are again 0 plus infinity plus infinity plus infinity. Not particularly interesting distances, but you have to do it. Okay, parents are initially -1 because -1 is some sentinel, which is not an ID of any of the vertices, right? You can use any sentinel you like, and you may assume like, why don't we use 0? Because our ID start at 1, and because we don't want ID start at 1, because we will decrement every ID by 1 in the code, just so that we don't waste extra space. And we can define vectors of adequate lengths of n and not n plus 1, right? So that's why we use -1 instead. It would be nice if you define like k const int k sentinel vertex, right? And assign -1 to it and use this very long name all the time. And it's definitely the way to go in production code. But in contest, you don't want to write a long name so that often. I mean, I can afford it, okay? Because I mean, it's not really contest. I'm just training. And as you're training with me, you can also afford yourself long variable names. But as the actual contest, if you want to write P instead of parent and D instead of distance, it's obviously okay. You don't have to think about it. Okay, so initially our priority queue contains 0 and 1, so the distance to start and start ID. And then we process the edges. We have two edges outgoing to second vertex and fourth vertex. Both of these are better than plus infinities. So we update. We update the distance here to 1 and here to 4. We erase this pair from the heap, or should I say extract it as a minimum element, because again, we cannot extract and erase arbitrary elements from the heap. So we insert two pairs 1, 2, because 1 is the current distance to vertex number 2, and also 4, 4, because 4 is the current distance to the last vertex, all right? And because we updated the differences, the distances, we also update the parents. So currently, the shortest path to vertices 2 and 4 look like that, and parent on this path is 1. All right, all right. So then we take the next, extract another min. It's distance 1 and vertex 2, and we take a look at all outgoing edges, except those that lead to already visited vertices. Right? So first vertex is marked as visited, somewhere potentially in an external array. All right, so the only new edge, so going to the unprocessed vertex yet, is edge from 2 to 3 of length 2. The resulting length will be 2 plus 1, which is better than plus infinity, right? Okay, everything is better than plus infinity. On plus infinity, in case you're wondering, if your algorithm terminates with the result of plus infinity, it basically means that you have some unreachable vertex, right? This vertex is clearly unreachable from the first one, and the distance will stay plus infinity forever. So yeah, we processed this vertex. We also updated the parent of this vertex to second vertex. We erased min, and then we go on. So we inserted a pair 3, which means that the current distance to vertex number 3 is 3. And then we process this pair, it does not improve distances, and we process this pair, it does not improve distances as well. Now, potentially, I mean, you can have multiple pairs. So for example, if the length of this edge was 0, which is kind of not great, but algorithm deals with this just nicely. Then while processing 3, 3, we would obtain pair 3, 4, which means that the current distance to vertex 4 is now 3, and the parent will also change to 3. So we would insert another pair corresponding to vertex 4 into our priority queue. Then we would take it from extracted as a minimum element. And once we do it, we would take another pair corresponding to vertex 4, but we would not process it because this element does not agree with what we have in the distance, in the current distance. It's greater than the current distance, which means that it's an outdated pair. It corresponded to some path that was shortest some time ago, but is no longer the shortest one. We just discard these pairs. We don't iterate our outgoing edges. And I believe this is all you have to know about sparse Dijkstra. You can also have a version with std set, but again, it's slower. Yeah, I believe I covered everything I should have. But if you have any questions remaining, you definitely let me know in the comments below. I will try to answer them all. I believe I answered most of the comments on the YouTube channel so far. So yeah, I mean, at some point in the future, we will have some sort of live streams so that you can ask your questions immediately. I'm currently working on setting any streaming platforms like Twitch. Once I do, I'll let you know definitely so that you can join and ask questions in real time and have to communicate through comments. But comments are also fine. So if you can't make it to the stream, to the future live stream, you can always ask in the comments later. I will go through them. I mean, we don't have like 1 million subscribers, so it's possible to go through all the comments, and I will definitely do it. All right. So there's one last algorithm that I would like to cover before we go to actual code. And it is, of course, the Ford-Bellman algorithm. Excuse me, Ford-Bellman. And if you think about it, like it may seem a little bit strange at the very beginning, because in the Dijkstra algorithms, no matter which version we use, we assume that all edge lengths, no matter what edge it is, the length of the edge is non-negative. And it kind of makes sense in case distances denote lengths, right? Lengths of some physical objects like rods, or I don't know, or maybe we have some sort of, or maybe cost of road construction or anything like that. Or maybe cost of directing the traffic through some road network, right? But yeah, actually directing traffic is some sort of mean flow, right? And we will cover it a little bit later. But for most reasonable problems that you can think of, distances are non-negative. But sometimes this is not actually a distance, it's a cost. And it may be indeed beneficial to build some roads. I mean, you will spend money doing it, right? But for example, you will connect some important parts of your city, decrease the traffic load, anything like that. So it may be in the long term beneficial to build roads. Or any sort of other connections. Like for example, you're building some sort of network at your company. I mean, computer network, right? It may be beneficial to add extra connections. For example, reserve one, right? So for when something fails, the entire network does not fail. It may be also beneficial to build something. So yeah, in some cases, distances can be negative, and Dijkstra has fundamental flaws preventing it from working with any sort of negative distances, because it assumes that paths can get shorter, right? When I had that argument about red path from start to V and blue path going through T, we assume like, oh, well, if the red is longer than the entire blue, then it's also longer than this part of blue from S to T. But if this edge length is, for example, minus 100, right? And you can have like 1 here and 10 here. Obviously, this argument doesn't work anymore, and so does not the algorithm. So a better algorithm is needed, as one being capable of processing negative distances. And it is indeed the Ford-Bellman algorithm. Now the algorithm works as follows. Let me pull just in the case that you want to read, as I explained it. So it is also an iterative algorithm, and the way I encourage you to think about iterative algorithms is that they obtain a partial solution to the problem at every iteration, and these partial solutions gradually improve over the number of iterations. In case of continuous optimization, you don't have to converge, but in case of discrete optimization, which is our problem, or all graph problems are discrete. Well, yeah, I'm wrong. Like, shortest path problem is discrete. Then after some number of iterations, we converge to the correct result. And it turns out that Ford-Bellman again works in n iterations, or should I say n-1 iterations, because it uses the following fact. So the key fact that in the proof of the algorithm is that after first k iterations, we correctly process all paths that are at most k edges long. So not necessarily this length of the path measured in terms of edge distances, edge lengths, is at most k, but the number of edges is at most k. So we have 1, 2, potentially some more edges in k. Potentially smaller than k, right? So I can have like k minus 17 edges. All of these paths will be processed by the end of k iteration. And because they are all the paths in the original graph, it makes no sense to go twice through one vertex unless you have a negative cycle. A negative cycle we will call later. So currently we assume that there is no negative cycle in our graph, and it makes no sense to visit one vertex twice, because what are you doing? You kind of having external loops that do not speed your path up, right? You're kind of looping around, like obviously having an extra cycle in something like a biathlon does not speed you up, right? So you don't want to do this. If you don't have like this negative length cycles, then all paths are of length at most n-1, because there are n vertices, and the number of edges on the path is one smaller. So we have 1, 2, 3, 4, 5. Let me assume that this is one edge 6. And then we have 1, 2, 3, 4, 5, 6 edges. Because of that, you can't have more than n-1 edges in any path. So by the end of n-1 iteration will be done. And iterations are fairly simple. On every iteration, we iterate through all edges and try to decrease the distance over every edge in the same fashion as we did before. So when we're processing the edge from V to W, I believe I can write these letters better. So from V to W, I'm terribly sorry, it's not all that convenient to draw with my mouse. I will try to think of a solution, but I think for the most part it works just fine. So we try to update our distances like that. And potentially like this is negative, so distance to W can be smaller than distance to V. That's okay. Like this happens. For example, here's distance to T is 10, but distance to V is -90. It means that building a rod from T to V is very beneficial in case you're wondering about some sort of physical explanation. And something like that. So yeah, and Yeah, so you just iterate over all edges on every iteration. So the resulting complexity is clearly O of n, big O of n times m, which is not great in case of dense graphs, all right? Because m can be up to n squared, and then we have something like n times n squared, which is n cubed. And not all that great, but kind of you don't have another choice when you have negative lengths. I mean, on the beginner level, at least, and intermediate as well. I think there are some like a bit better algorithms. I'm pretty sure that there are algorithms that run faster on average, or something like that. And yeah, usually a shortest paths in Ford-Bellman algorithm are not very long in terms of number of edges. For example, if your graph has small diameter, it means that like every vertex can be reached from starting in, let's say, 10 steps, right? So you are starting from the city center, and you can reach pretty much everything by taking one highway and one secondary road and one small street, and you are basically at the destination point, right? So you don't have all that many edges. Then you can definitely don't do entire n-1 iterations. Once your distances stop changing, you're done. Once the distance stops changing, you are done. You can stop regardless of whether or not you're already done n-1 iterations. Now, there is one last problem. What if we have negative cycle? Negative cycle, you can loop through it again and again and again. And basically, if you have like a source somewhere here and destination somewhere there, then an optimal way to travel from S to D would be to there is no optimal way, because you can always make one more cycle, right? Do one more iteration of this negative loop. It's not great. So in good graphs, this doesn't happen. In Olympiad problems, it does happen because it's a kind of good test case. You can detect whether or not this happens by running another iteration. So like, we believe that if such thing does not happen, we can prove. And by the end of n-1 iterations, all distances should be correct. And if afterwards we make another iteration and we find that something changes, and obviously this distance is not correct because there is a negative loop somewhere. In this way, you detect the negative loop, the existence of negative loop. If you want to find all vertices with a negative cycle between source and destination, there are different ways to do it. I did it in a very lazy way of doubling the number of iterations. And I believe that then any distance that changes during the next n iterations is obviously incorrect. So you can set it to minus infinity because there is no optimal distance. And I also believe that any vertex for which distance is indeed minus infinity is detected in another set of n-1 iterations. Well, because you kind of extend what happens. Like if you have like +1 here, -3 here, +1 here, then on the first iteration after on the nth iteration, this vertex will be marked. Then you detect that, wait a second, this path decreases distance to this vertex, then to this vertex, etc. And obviously, in this way, all the edges, all the negative infinity distances will be detected within another set of n iterations. Again, it's not the fastest way to do it, but it's asymptotically the same. If you have negative loops and the negative cycles, then you have to do all the iterations because distances constantly decrease. And if you've done like n iterations already, it doesn't really matter if you do another one or another n, all right? So asymptotically, it's the same solution, but it's kind of fast to implement. You just copy paste your code, adapt it, and you're ready to go. So let me clear this up and we'll go quickly through some implementation details. Now, I defined a nice function that reads a graph as adjacency matrix from the input. It's nice and smart here. Just the usage of autoreference, not to have, allows you to iterate via range-based for loop. So you don't have to remember about anything about the index. And the reference is necessary to indeed change the elements that you're going to change. It's also a nice practice to have a parameter like input stream. This way, for example, you can use the same function to read directly from files. I believe if you open file stream, or actually you need to put if stream here. But if stream is a subclass of ifstream, so it should work. Yeah. But I use stdf reopen anyway, so just a good practice to provide alternative ways of input, right? Then we have, also using, you can define your custom types very conveniently using statement. Kind of, yeah. Fancy sentence here, but whatever. So I don't like to write std vector int all the time. Even if of course I know you can use an name space std and don't have to write std all the time. But again, a vector of ints is how many characters? 6, 12, 15, 19. And you can just define graph once and then you save 14 characters all the time you write it. C++, you don't worry about long variable names, you worry about long type names, unfortunately. But it's okay. Also, once you define the function, you can use like auto. So you don't have to write output type any time. So I also use const just to ensure that I don't change these things, because I sometimes accidentally change something in the functions that I don't want to, because I don't always write readable names. Unfortunately, sometimes I mess variables up and change something that should not be changed. By writing const every time I can, I decrease the number of such errors. Yeah, we have, it's a array version of Dijkstra. It uses distance array, Boolean array of use. Original distances are infinite and used is false, distance to a source of 0. And we make total of iteration count iterations. We select the closest unused vertex. I believe you can do it in a better way. Kind of, There must be a way in C++ to conveniently filter distance by used and then select mean element, but I don't necessarily care. I mean, it's like what? 7 lines of code? I think I'm okay with it. Then we process all outgoing edges and also if the current closest distance is infinite, it means that we are trying to process unused vertices which are unreachable. It doesn't really make sense to process them. We just can break straight away. And also it would be bad to do it because, again, edge length is something positive. You add to positive infinity, you get something around negative infinity. So this else branch is kind of must have in this case. In terms of distances, and I don't care about early stopping when you stop wherever you hit, wherever closest vertex is destination. You can add it to the code if you want to. I just output closest distance. Yeah, except with sole exception that output format specifies -1 for unreachable, and I have plus infinity. Yeah, it's okay. So yeah, nothing really interesting here. The only thing you have to keep in mind it's convenient to have zero-based indices of vertices. So that's what we do. Decrement vertex ID wherever you see it, you'll be fine. Also, a couple of asserts can help validate input. So for example, I've changed source and destination. I obviously like 99% sure that I did it correctly, but I can have an assert, and if it fails with runtime errors, then I have a little bit more information for debug instead of if it failed with something like wrong answer. If it failed with wrong answer because I didn't decrement source ID, it will be very painful to find it out. But if it falls with runtime error, and I'm pretty sure that I'm good with memory, and I definitely know that this is one of my asserts for, and I can like verify each of them manually. Look at it closely and yeah, see if there's any error. Or of course, you can write your own test cases from your programs in debug mode, but it's not something you always have time for in the contest. Yeah, so nothing more interesting for the first problem. And the second problem is for sparse Dijkstra. Also, graph is now present as an edge list. We can define another type for edge, which will be just pair. Yeah, I think I will actually do something with that. Or is it too much? I don't think it's too much. I think it's fine. I mean, my face probably goes somewhere around minimap, so it doesn't cover anything. You can see most of it. Yeah, so it's a version of Dijkstra which uses heap and also computes parents. Not the best choice of architecture here, but we have what we have. Again, convert IDs, read graph, compute the distances and parents. Very convenient structured bindings. Really like modern C++ features. I remember that someday in the past, you had to first define variables, and then you had like std tie, distances, parents, gets, and you, in this case, you obviously also need to write type like std vector. Yeah, not really convenient. It's just so much better structured bindings. Yeah, also here we have to retrieve the path. So we do it in the following fashion. We start with destination and we repeatedly go to parent of the last vertex until we reach the source. So parent array effectively allows iterating backwards along the shortest path. And then we have just to reverse the path. Simple as it gets. And also, whenever you decrement, you have to remember to increment it back again. A way to do it would be to assert like vertex. I mean, if you were thinking that this version as well, then you can always have asserted of something like that. So you know that vertex ID that you're about to output should be greater than 0, and at most vertex count, you would have something like that, and it would fail because you have 0, right? So it again shows the importance of vertex IDs. And these asserts, you can turn them off, that they don't get executed when built as release. They only get executed when built as debug. So that they don't take all that much time. Okay, going back to reading graph, there is nothing interesting except that you have to add boss edges to the graph because it's undirected. Also remember to, well, actually, I was changing my code after I submitted it. Now it appears correct. Because, yeah, initially I was thinking that it's directed, so I used source and destination, but these things don't really make sense when the edge is undirected. So first and second are perhaps better. Now, the extra heap is not interesting at all, except for the usage of priority queue, because by default, priority queue provides access to the largest element, I believe, and you want to the smallest, so you use std greater. Obviously, if you were to define like a reasonable name for type, for pair of integers, I don't know. Yeah, it would be a little bit more convenient to write it this way, right? Now you can at least fit it on the same line, all right? Yeah, I'm not exactly sure whether or not you can have it like inside of a function. Probably not. Probably you can have it inside the class. Yeah, 100% you can have it within a class or namespace, but I'm not sure about the function. I think you can't. But either way, you can just put it outside, right? But I'm okay with writing things like that. Again, like the point of writing reasonable code at such trainings is that you can later add this to your template and don't have to retype it again. And if you ever have to, you can shorten the names, right? Now with heap, it's the same thing, that you just select closest unused vertex in big O of log n, and yeah, you can definitely make it constant so that you don't accidentally change close distance and closed vertex. For example, somewhere around here, I believe I mistyped something, or probably, okay, somewhere I mistyped something and got a compile error because I remember to put const. Basically, everywhere you can put const, you do. You should 100%. You can avoid all that many errors with writing const wherever you can. Yeah, as you can see, I needed a little bit of debug. Yeah, it was just the wrong answer on sample, and a couple of minutes later, it was fixed. Yeah, you iterate over outgoing edges. You can do it conveniently, right? Because graph now contains pairs, so you can unpack them immediately. You get adjacent vertex, you get the length of the edge. You check whether or not you can update. If you can, then you update parent and distance and place another pair here. Notice that you don't erase any pairs, other pairs associated with adjacent, they will be discarded here. If you obtain the pair from heap that has invalid distance, it will be detected here, and you won't process it. Else, this is a fake pair. So you don't process fake pairs. And also, once you start processing unreachable vertices, you can stop. And you should stop, because otherwise you will have like k infinity plus 1, and you'll break. This is again mandatory here. And you can conveniently return, like you don't have to write make pair, you just can have for brace initialization, some sort of. And it's all for this problem, I believe. Kind of instructive points are to bring vertex IDs back, to remember to write STG greater here in the heap, to insert boss address, and to write const everywhere you can. So it solves so many problems. You won't believe it. The last problem is about for Bellman algorithm. I almost accidentally said Ford Fulkerson. Was about to say like what you're doing today. No, Ford Fulkerson is for another day. For Bellman algorithm. Here, the only tricky part is accurate processing with k minus infinity. The graph is really small because obviously you need a lot of time. You need big of n times m. So you have 2000 vertices, 5000 edges, some source vertex, and you want to compute shortest path to all other vertices. In case you have a negative cycle, you output 1. In case of unreachable, you output 2 star, whatever that means. We are totally fine with it. We can grab reading graph edge list from the previous one. And the only difference is that we don't have to insert bus edges. Ford Bellman again works with a graph, and notice how we don't copy and we ensure that graph is constant indeed. Graph is still the vector of vectors of edges, only difference is that now weights of the edges are long integers, because they can be up to 10 to the 15s according to the problem. But we don't care about that because there are at most 2000 edges, so 2000 times 10 to the 15 does not overflow in long integers, of course. Again, the main function is as easy as it gets because you have nice templates, right? You can fit entire main function on the same screen. If you and half of it is written input, really. Here you read an input. Here you're solving the problem. Very convenient to have reasonable function structure of your program. So you obtain distances, so you look all possible destination. If the distance is infinite positive, then you output star because it means unreachable. If the distance is negative infinity, it means you have negative cycle. You output minus. Yeah, and well, you can have something like that, but I just wanted all of these three statements look kind of the same way. So, otherwise, the distance is actual distance, and you just output it. For Bellman, again, first phase is regular distances when nothing is infinite. Well, something can be positive infinity. If the vertex is unreachable, then you should not change the distance. You just min relaxate as usual. Distance to adjacent, get minimum of distance to adjacent and distance to vertex plus edge length, where adjacent is adjacent to vertex. On the second iteration, it's almost the same thing. You just if the distance to current vertex or if the distance to adjacent changes, it means that adjacent there is some sort of negative cycle. Or if the distance to a vertex is minus infinity, then distance to adjacent should be minus infinity as well. As easy as it gets, really. Notice again the fine usage of constant alpha so that you don't accidentally change adjacent or edge lengths in the process. And constant is pretty important because you have a reference also. So you have a vector of vectors of pairs. So graph is a vector of vectors of pairs. A graph at vertex is a vector of pairs, and you don't want to copy pairs all the time. So you use reference, and you also don't want to accidentally change anything, so you use constant. I'm not exactly sure whether it's like an algorithm lecture or nice features of C++ that will save you from dying 100 million times lecture, but either way, I hope it was useful. And I really hope it was helpful for you guys. I mean, I believe that interest, some sort of recent interest in the channel, proves the point of it being helpful. And we will definitely have more of this soon. So yeah, definitely come by and watch whenever you have time, whenever you need to refresh some sort of theoretical knowledge, or whenever you need a walkthrough for any of these problems. As you can see, we covered problem set 6 and 2 already. I believe 2013-2014 season has a total of 10 problem sets, and we will cover them all. I mean, over the next kind of 2 or 3 weeks, we will definitely cover them all. So stay tuned for more. Let me know which one of the problem sets you would like to see next. I'm currently thinking of minimum spanning tree, but we may have something other, something different. So yeah, thanks for watching. Hope you have a great time, and bye for today.